Welcome to Lab 3. The purpose of this experiment is to analyze a star's motion orbiting a black hole and estimate the mass of that black hole. We have used the following physics principles and formulas for our experiment. Newton's second law, or the momentum principle, which states that the net force is equal to the rate of change of momentum. Newton's universal law of gravitation, which has been found between the black hole and the star. Newton's law of gravitation states that the force of attraction between two masses is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. The capital M here has been taken as the mass of the black hole and the small m has been taken as the mass of the star. Here we can see that the net force is equal to the gravitational force as we only consider the force by the star acting on the black hole. The parallel and perpendicular components of the force state that the net force is equal to the F net parallel plus the F net perpendicular. We have made the following assumptions in our experiment. This is the code that we have used to perform our experiment. The email ID has been changed to my own unique email ID. Here we can see that the gravitational constant is 6.7 into 10 raised to power minus 11. The mass of the star is 2.0 into 10 raised to power 30 kgs. And the delta t is 86,400 seconds, which is equal to 24 hours or a day. In our code, there are two lists that are used to calculate the velocity from the data. The first loop is being used to store values inside the lists. In our second loop, the main changes and calculations are being performed that are used to calculate the net force from motion data. The value for final and initial velocity are depicted here. To calculate the final and initial momentum, we have multiplied the star's mass by the final and initial velocity respectively. To find the change in velocity, we have used the formula delta V is equal to V final minus V initial, and similarly for change in momentum, we have used the formula delta P is equal to P final minus P initial. And then we have used Newton's second law to calculate F net and equate that value to rate of change of momentum. To calculate the parallel and perpendicular components of rate of change of momentum or net force, we use the following formulas. We first found the unit vector for momentum and then found the magnitude of the rate of change of momentum. Using this, we then were able to find the parallel and perpendicular components of net force or rate of change of momentum. This is the formula for Newton's universal law of gravitation, which we have used to calculate the mass of the black hole. We have used the arrow scale that is equal to 1 into 10 raised to power minus 17, which determines how long to draw the arrows that represent the vectors. This is mainly for visual purposes only. Finally, the values that get printed are equal to the magnitude of F net parallel, and F net perpendicular, and finally the average mass of the black hole is printed. We can run this program to see the output. Here we can see that the orange arrow represents F net, the blue arrow represents F net perpendicular, and finally the magenta or the dark pink arrow represents the F net parallel. We could see that the F net parallel was in the direction of the motion of the object, which is the star, and the F net perpendicular is in the direction which is towards the center of the kissing circle. After performing all the calculations and running the program, I found the range of the black hole mass and the average mass of the black hole, which are both mentioned here. The 424 mentioned here depicts the number of iterations of the while loop. These are some of the sources of errors that may have made the values in this experiment a little less accurate. Now, to answer the first lab question, the difference between the net force and the rate of change of momentum. F net refers to the sum of all forces acting on a particular system which leads to a change in the momentum and hence the motion. The rate of change of momentum explicitly or specifically refers to the change in speed and or the change in direction of the system with respect to change in time. Although numerically and according to Newton's second law, these two quantities have the same value, they represent two different things. Calculating these two quantities is done in different ways. The net force is calculated by the gravitational force between the star and the black hole in this experiment, and the rate of change of momentum is calculated by the change in velocity. Now, the answer for the second lab question, the what if question. We will not be able to specifically tell the difference between the mass of the new black hole and the mass of the initial one. However, If all the conditions, like the motion and the location of the star, remain the same, the gravitational force will hence be the same, because of which we can say that the mass of the new black hole will be the same as the mass of the initial black hole. Conclusion. We were able to estimate the mass of the black hole using Newton's second law, the parallel and perpendicular components of rate of change of momentum or net force, and Newton's universal law of gravitation. We found out that the mass of the black hole is 1.03335 into 10 raised to power 34 kgs. Thank you for watching.